We're going to generalize what we did last time, and we're going to discuss a method for approximating integrals that will give us a asymptotic series approximation to the original integral. So the integrals we'll be interested in today will take the form be some integral of some function of w of the integration variable times e to the z f of w dw. So this is similar to the type of integral we considered before last week, where we had some parameter that was in the exponent times a function of our integration variable. And we were interested before in the limit that z is large. It'll be slightly easier to work out the asymptotic series expansion in this, for the case where the parameter is large, but we can always just set z to be 1 over lambda if we're interested in a small parameter. So the method we're going to study today applies equally well to the case where we're interested in an integral that's some function of a small parameter, which will very frequently be the case in quantum field theory. So many of the objects we're going to study in quantum field theory will be integrals of this form. The one difference between what we'll do in quantum field theory and what we're doing today is that today we're going to consider integrals that are single integrals that only have a single integration variable. And quantum field theory will have infinitely many. But apart from that difference, this is basically the type of integral we'll be studying extensively in quantum field theory, particularly in QFT2. And in general, we might be interested in not just real integrals, but complex integrals, so where C is some contour in the complex plane. Even if we are interested in a real integral, sometimes in order to apply this method, we'll have to deform it in the complex plane, and we'll see an example of that later today. So we'll start out by assuming that our integral is some complex integral, not necessarily over a closed contour, but some integral in the complex plane, and it applies to the special case where it's a real integral as well. So this is the integral we want to approximate. And yeah, in QFT, we're often working in Minkowski space where there'll be an I in the exponent. So in that case, things are complex. So in general, we do need to consider the complex case. And the method we're going to use to approximate this integral is a generalization of what we did last time. So last time, we didn't have this factor out front, and it was a real integral. But basically what we said was that when our parameter became large, this integral was dominated by contributions near where f is maximized. So where the integrand is large, if f changes by a little bit, if z is large, then the relative contribution a small distance away from where f is maximized will be negligible. So we only need to consider a small region around where the integrand is maximized. So what I just said is the whole story if it's a real integral. If things are complex, well, we need to see what effects that has on that argument. So if the real part of f is maximized, then the magnitude of the integrand will be maximized. So we expect the argument still should work if we consider regions near where the real part of f is maximized.
That z goes to infinity, z goes to real infinity?
For now, we're going to consider z to be a real number. We will relax that assumption later. So near dominant contributions we expect should come from the region near where the real part of f is maximized, and I'll call that u. But even if the real part is maximized, if the imaginary part of f is not constant, then as we do an integral in a small region near where the real part is maximized, the phase of the integrand is going to be changing rapidly. And in general, we expect there to be destructive interference. So in that case, even if the real part is maximized, if the phase of the integrand is changing, we have no guarantee that the dominant contribution should come from this region. So, but this should work though if the imaginary part of f, which I'll call w, is constant. Otherwise, there will be destructive interference. So this point is key. If we don't put any restrictions on what the phase of the integrand is doing, there's no systematic way that we can approximate the integral. We might get destructive interference in some region, and there's might be some other region where the real part is smaller, but maybe the destructive interference is less severe. So analyzing the problem will be very complicated unless we impose the condition that the phase is constant. And so in general, the first thing we want to do if we have an integral of this form is we want to deform our contour into a constant phase contour. If we do that first, then we can basically apply the method we looked at last time when we studied Stirling's approximation, because the phase then will be constant, and we can just look at where the magnitude of the integrand is largest. So this means first form contour into constant phase contours. Okay, so let's suppose we've done that. Let's suppose that C, maybe even if it's not the original contour that we're interested in, it's some equivalent contour we've deformed our contour into such that the contour is a constant phase contour. Then we can use the approximation that we did before and approximate the integral in a small region around the maximum. And so let's suppose our contour looks something like this. And W naught is the point where U is maximized.
Here we are looking for the global maxima or any local maxima we have to take into account.
Any local maxima.
Have
So
to be taken into account.
yes. So if well, it depends on the order in which you're going to try to construct your asymptotic series. If you're only interested in the leading term, then the global maximum will be the only one that will contribute to the leading term. It'll be dominant over the contributions of other maxima, but in general, we might be interested in constructing the first few terms in the asymptotic series. In physics, usually 2 terms would be enough, but we're often interested in the case where we want more than 1 term. In that case, we need to consider any local maxima. Okay, so since we're only interested in our integral in a small region near the maxima, we can linearize our contour in a small region around the local maxima. And so this dashed line is a linearized version of the contour we're interested in. And let's say this angle here is phi, and the distance along the linearized approximation of the contour is t, so that along this line, W is equal to W naught plus e to the I phi times t, where t is real. So in that case, that's linearized version of the path, and we'll use that to construct a saddle point approximation to this integral. So what do we know about this point W? So the point W is a local maximum of the real part of F. So at the point W naught, the gradient of the real part is 0, which tells us by the Cauchy-Riemann equations that the gradient of the imaginary part is 0. So this point W naught is a saddle point, a complex saddle point of the function f. So if we have an analytic function on the complex plane, the real part and imaginary parts always increase in different directions. So if we have a place where the gradient of either the real part or the imaginary part vanishes, the other one also has to vanish, and that in the complex plane that will look like a saddle point where in one direction, the function will decrease, and in the other direction, the function will increase. So this means that W naught is a saddle point. That's where the name of this approximation comes from. So this is point F, and along the curve C, we know that the gradient of the imaginary part is perpendicular to the tangent vector t, which is in this direction. T is here. But the gradient of the imaginary part is always perpendicular to the gradient of the real part, so that tells us that the gradient of the real part is parallel to the tangent vector. So this contour in near the saddle point is leaving the saddle point in the direction where the phase is constant, but also in the direction where the real part is decreasing as quickly as possible. So this is the steepest descent direction. And this method is also sometimes called the method of steepest descent for that reason. Okay, so we want to approximate our integrand in a small region around W naught. And to do that, as before, what we can do is expand f in a Taylor series near W naught. So f is f of W naught plus half W minus W naught squared times second derivative f W naught. We could go to higher order if we wanted to. But for now, let's stop at second order. So the key difference for this integral compared to what we did before is now these are complex numbers. So it'll be useful to reduce what we were doing now to the case that we looked at last week, to rewrite these in terms of real numbers and phases.
So what was again the conclusion there? So the gradient of the real part is parallel to t, and why does that mean that that's the direction of steepest descent? I mean the gradient of u minus the gradient of u is always the direction of steepest descent of.
That's right.
Of u, right?
That's right. So locally we're going near W naught. We're going in the direction where the phase of f is constant, or where sorry, not the phase of f, the phase of our integrand. The imaginary part of f is constant, and the real part of f is changing as quickly as possible, which means that the magnitude of the integrand, which is e to the f, is changing as quickly as possible. So,
and why is it called descent? Well, not steepest change. I mean, because on one way you're descending and the other you're ascending.
Well, um, this will be the saddle points that will provide the dominant contribution will be local. The real part will have a local maximum. So it'll be going down in both directions. Okay, so we want to expand f, which is the exponent of the integrand. But it's more useful to write this in terms of these angles and real numbers. So then we can reduce it to the case we had before. So we can write this as is 1/2 w minus w naught squared times, let's call delta the phase of f double prime. And write this then as the magnitude of f double prime. And what we want, so that we can reduce it to the case we considered before, is we want this to be equal to minus 1/2 t squared times f double prime w naught squared. Because then it just locally looks like a Gaussian integral, just like before. So if this term looks like that, this term's a constant, so we can just pull that out of the integral. This is all in the exponent. So if we plug that in the exponent, we'll just have a Gaussian integral. Which is exactly what we did before. And exactly what we'd expect, any function that's highly of this form, that's highly peaked, should look locally like a Gaussian. So if we want this Taylor expansion, the first term to be minus 1/2 t squared f double prime, that tells us that, so we know what the phase is here. So this w minus w naught is e to the I phi times t. So what we get here is a e to the 2 I phi times e to the I delta naught is equal to minus 1. And that's just the keeping track of the phases. We have the factor of t squared of w minus w naught. So this tells us that 2 phi plus delta naught should be equal to plus or minus pi. And the plus or minus will be determined by global considerations. But ultimately it won't matter. We'll use this relation later to simplify our results.
But that relation, I mean, we cannot impose that, right? Delta 0 is coming from f double prime, which we know how to calculate, and phi is coming also from the lines of constant imaginary part of f, right? So delta 0 and phi are already fixed.
They are fixed, but we fixed phi exactly so that this relation holds. We fixed it so that this integral had a constant phase, and so that basically we could rewrite it as some constant, which is here, times a real integral that is highly peaked at w. So this this is a consequence, basically, of choosing our constant phase contours where there's no destructive interference. That guarantees we can write it as just some overall phase times a real integral. Okay, so let's plug this Taylor expansion in to I. What we get here is E Z F naught. That's just the first term, the overall phase. Then we can say that our integral is approximately, it was dominated by this small linearized region, and let's say that this linear approximation is good just in some small region where t goes from minus t1 to t1. We have g of w naught plus e to the I by t, e to the minus z over 2, t squared, absolute value of f double prime w naught, dw dt, evaluated at t naught dt. That's just the change. This just comes from the change of variables from originally integrating with respect to d. Now we're integrating with respect to t. Okay. So
what's the T naught? Where is T naught?
T naught
dw
is
just e to the I5?
it should be 0. Sorry, not t naught, just 0. So when t is 0, w equals w naught.
But that derivative is always e to the I5, right?
That's right. So this integral, we can evaluate that factor, e to the I phi. So this integral is linear for just a small region, but we wouldn't change the result of this integral very much if we extended the integral instead of from minus t1 to t1 to minus infinity to infinity, because we're interested in the case where z is large. So if t is very different from 0, then this integrand is tiny. So it doesn't matter if we extend the limits of integration. So we're just adding a negligible contribution. We can also expand, so we can extend the limits of integration. We can also expand g. So we can write g as g of w naught. We could add other terms. And this change of variables is e to the I phi, as just pointed out. And so now we've written our integral as a Gaussian integral, which is an integral we can do. And we'll see, get some extra practice doing Gaussian integrals and variations of them in tutorial later this morning. But this, in particular, this first term is exactly just the ordinary Gaussian integral. And so we get, as our final result, is an asymptotic series, valid as z goes to infinity. Our first term is just gives us 2 pi over z, e to the z f naught. And over here, in the denominator, we get minus f double prime with no absolute value. So here we have an absolute value of f double prime, but we also have e to the I phi. And so by combining the phase with this relation, we can eliminate the absolute value. And then our first term will be just g of w naught, and we could add each of these terms in the Taylor series for g. Also gives us another term, but the first term would be something that's suppressed. An extra power of 1 over z compared to the first term. There's a minus sign. And the absolute values, I'll cancel out here as well. We go to higher order in G, but eventually higher orders in F become more important. But for the most part, we'll generally be interested in just the first or first 2 terms, in which case we don't need to worry so much about these additional terms. So, well, considering the phase, what's crucial in the consistency of the approximation, the phase completely drops out of the final result. So none of the terms in this series will depend on the phase. So once you've determined the correct contour where you can apply this method, you don't need to worry further about the phase. But it is essential. Making sure your contour is a constant phase contour is essential for applying this method. So we'll look at an example now where saddle points that aren't on the original contour can contribute because the original contour is not a constant phase contour. And the converse can also be true. We can have saddle points that are on the original contour that don't contribute because once you deform the contour into a constant phase contour, those saddle points will no longer be on the contour. So the constant phase contours are crucial for the consistency of the approximation. And that's because they tell you, they answer the question, which saddles are relevant. Not because the phase shows up in any way in the final result. So that's the general method, and we'll move on to an example of how to apply it. Unless there are questions or comments. Yes.
Can we use the same kind of method if we are not a function of a variable, but if I is a functional, for example? Or...
Yes. We're going to essentially use this method all the time in quantum field theory. There will be, it's the same idea, we will essentially be taking integrals of this form where instead of ordinary integrals, they're functional integrals. But we'll still be doing the same thing. We'll be approximating the integrand as being only large in a small region around where the integrand is peaked. So, and we'll be performing a Gaussian approximation to those integrals. So the idea is the same. There are, because they're functional integrals instead of ordinary integrals, there are a couple additional details we'll see in the quantum field theory courses, but conceptually it's exactly the same thing as we're doing. And technically it's very similar. Okay. So let's look at a particular example to see how to apply this. And this example will illustrate a couple of neat points, things that can, interesting things that can happen when we apply this method. So the integral we'll consider is this following real integral. And let's suppose we're interested in this integral for z large and z real. Okay. So the first thing you might think when you're looking at this integral is, well, it looks like it's already of the form considered before. It's got an exponential with z and some other function out front. But you need to be careful here because this extra function out front is independent of z. So if we tried to use this method just directly considering this cosine as g, we'd get the wrong answer. And that's because, well, this exponent is large when t is, so this part is large when t is smaller than or about 1 over z. But when t is about 1 over z, this cosine is oscillating very wildly. The argument here, this is a z, is large, and so the cosine is oscillating, and we've got destructive interference, which is exactly what we were trying to avoid when we were deforming our contour to a constant phase contour. So So we can't directly apply our method to this integral. We need to manipulate our integral and put it in that form where all of the z dependence is in the exponent. If we do that, then we'll be guaranteed there's no destructive interference. So we can do that by noting that I of z is the real part of the integral e to the minus 4 zt squared plus 5I zt minus I zt cubed. Which by symmetry is a half the integral from minus 1 to 1 of the exponent of the same thing. And we can write this as 1/2 e to the minus 2z times the integral from minus 1 to 1 dt e to the z times rho of t, where rho of t is minus t minus I squared minus I t minus I cubed. So all I did was just factorize this polynomial and pull out the constant factor. It's not essential that I did that, but it'll just slightly simplify things for later.
You still need the real part of that, right?
No, so the real part, so in this line it's the real part, and then the next line I extended the integral from minus 1 to 1 and dropped the real part. The imaginary part will cancel by the t to minus t symmetry, and we'll get twice the real part, so that's where the factor of half comes from. So now this integral is of this form, and we can apply our method. So what we need to do in order to apply this method is identify the constant phase contours. That identify a constant phase contour that's equivalent to the contour we're interested in. And then, well, we don't have to go through this again because this formula is general. At least the first two terms. If we wanted to go higher order, we'd have to be careful about when f became important relative to g. But if we're just interested in the first term, there's no additional calculation we need to do besides taking a few derivatives after we've identified the correct contour. Okay, so the reason I wrote the exponent in this form is it's easy to see at least where 2 out of the 3 saddles are. So there's this has where 1 out of the 2 saddles are. So this is a degree 3 polynomial, so it should have 2 zeros, and one of them you can read off directly. It's just at I. This has a saddle at t equals I, and the other one you can find by computing the derivative, and it's at 5I over 3. So let's sketch a plot of what our contour is and what contour we're going to deform it into is. So here's the imaginary part of t. Here's the real part of t. And our original contour starts at -1 and goes to 1. But this is not a constant phase contour, which we can see by noting that the imaginary part of rho of -1 is -4. So we just plug in 1 here and take the imaginary part, we get 4 minus 4. And at 1, we get 4. So this contour is not a contour in which we can apply the saddle point method. It doesn't pass through any saddle points, but even if it did, we could not apply the saddle point method. We know that there are saddle points at I and at 5I over 3. So what we can do is instead, we can plot the constant phase contours that go through our saddle points and our endpoints. And they'll look something like this. So these are the constant phase contours. These are the curves that solve imaginary part of rho of t equals constant. And what we see, we just look at these contours. We can immediately guess what the correct contour should be. So this contour is the contour we're interested in. That's equivalent to a contour that goes down over here, connects over at infinity, goes up this way through this saddle point, but not the other one, down over here, and connects back up over by infinity and goes over here. So that these two contours are equivalent because there are no poles in our integral, our integrand. So we can freely just deform this contour, the green contour, into the white contour. Yes.
How do we know that the two contours will connect eventually and then you can grind it back up?
So one way you can tell is if you just plot this more carefully, you can see that they asymptote to the same thing. That's one answer you can give. Another answer you can give is that there are some mathematical theorems that tell you that if you can always deform a contour into a sum of constant phase contours that goes through some number of saddles. So we know that it has to work for some contour. Like this, that has some pieces that go up to infinity and other pieces that go from infinity through a saddle to back to infinity. So we know there are theorems that I'm not going to explain, but that guarantee that it should work for some sort of contour like this, and by plotting it, we can tell which contour that is. Okay, so this is our correct. This is the correct contour. This is the contour we want to consider. And well, if we want to apply the saddle point method, well, we know what the contribution of this part of the contour is. We also have these parts of the contours that terminate on our endpoints. And now we know our constant phase contours are contours in which our integrand is increasing or decreasing very rapidly. So if our integrand was increasing very rapidly in this direction, then the integral on this part of the contour would be divergent. So that means that if this integral is going to give us the final result, the integrand should be increasing as we get closer and closer to the endpoint. And so the endpoint and the region around the endpoint is the most important contribution to this part of the integral. Along the saddle point part of the contour, instead, the integrand is largest here and decreases in both directions. So that's another reason we know that the integrand is decreasing as we go to infinity on this part of the contour, because as we get close to infinity, these two contours are just infinitesimally far apart. So the integrand is increasing. So we need to include this region, which we already know how to do. We also need to include these two regions in order to approximate our integral. So the endpoints contribute. And there's a theorem that tells us what the contribution of the endpoints is. So the theorem is we have an integral of this form, a real integral, basically a real version of the integral we had before. Then, as x goes to infinity, this integral is asymptotic to f of t over I x prime of t e to the I x psi of t, evaluated at the endpoints. And if you've heard of it before, this is a generalization of the Riemann-Lebesgue lemma, which says something about integrals of this form if this is a constant. And the basic idea behind this this result is, well, what we can do is we can take this integral and integrate by parts, and we'll get two terms. And the result of the theorem is that the boundary terms go to zero much more slowly than the other term in the integration by parts. And this holds as long as the right-hand side of the equation is non-zero. F and psi, f over psi prime and psi are continuous and differentiable. And the integral of the absolute value of f is finite. So under these conditions, we can determine the asymptotic behavior of this integral. And the endpoint integrals are exactly integrals like this, which have a boundary, where the boundary terms are the most important contributions to the asymptotic series.
Excuse me, can you say again what RH is?
Right-hand side.
Red.
That's our theorem, and that tells us, there's one additional constraint. We we also need that psi is not constant in any finite interval. And yeah, the idea behind this theorem is just that as x goes to infinity, because of the I here, this integral oscillates more and more rapidly and eventually goes to 0. And so applying this to our case, we've got an integral of this form. The endpoint contributions at t equals plus or minus 1 contribute minus 4 minus plus I over 68z e to the minus 4 plus or minus 4I times z. So I just plugged our integral into this form. There's just some algebra there, nothing.
The theorem, the integral in the theorem should be psi of t, right?
Psi of t, yes, thank you. Okay, so this comes from the theorem. And so there are 3 potentially interesting contributions to our integral, these 2 endpoint contributions and also our saddle point contributions. You compute the endpoint contributions from the theorem. The saddle point contribution contributes 1/2 e to the minus 2z root pi over z. This comes from applying our saddle point formula from the top board, just keeping the first term. Okay. So we have 3 potential contributions, but it's not justified necessarily in keeping all of them, because we know that this is just the first term in an asymptotic series. And if the next terms are much larger than, say, the endpoint contributions, then we're not justified in keeping these endpoint contributions without keeping further terms in this series. And similarly, if we just keep if one of these terms is the largest contribution, there'll be additional terms. This is just a leading asymptotic term. There'll be additional corrections to that, and we wouldn't be justified in keeping the saddle point contribution if it's much smaller than this, than an endpoint contribution if the saddle point contribution is much smaller than the endpoint contribution. So in order to get a self-consistent result, we need a consistent result without going to higher order in either series around the endpoints or around the saddle points. We need to determine which of these contributions is the biggest, which one is most important. And to do that, we can just take the limit as z goes to infinity and see which terms are bigger. So prefactors are not important. So the endpoint contributions go like e to the minus 4 plus or minus 4I times z over z. And the saddle point contribution goes like e to the minus 2z over root z. and this goes to 0, if z is real. Basically the e to the minus 4z beats everything else. So that's telling us that the endpoint contributions are much smaller than the saddle point contributions. So saddle point dominance. And so we should write that I of z is asymptotic. So at the level of calculation we've done so far, we're only justified in keeping this saddle point term. And so this is our result for the integral. Any questions on that? Okay. So without doing a lot more calculation, we can look at what happens if we take z to infinity in some other direction in the complex plane, say with some constant phase. And in general, as I briefly alluded to last week, asymptotic relations like this one are generally only valid in some wedge on the complex plane. And with the calculations we've done so far, we can see why that's the case. So, and Stokes phenomena refers to what we're going to see in a minute. So Stokes phenomena says that Stokes phenomena refers to an abrupt change in the asymptotics. And it's caused by an exchange in dominance in terms or new or terms becoming relevant or irrelevant. So okay. So what do I mean by terms becoming relevant or irrelevant? So we saw that the contour contained three possible types of terms, 2 endpoint terms and 1 saddle point term. As we change z, as we change the phase of z, we're changing which part of rho contributes to the magnitude and which part contributes to the phase. So the magnitude will be controlled by the imaginary part the real part of z times rho, which is not, if z has a phase, is not the same as the real part of rho. So as we change the phase of z, we're changing the contours. And what can happen is that saddle points can jump onto or off of the contours. So that's what I mean here by terms becoming relevant or irrelevant to the integral. So we can have saddle points that jump onto or off of our contours as we change the phase of z.
But in our former discussion, only consider z is real. So how do we consider z has some angle not real?
So if we wanted to consider z having some phase, so if we wanted to take z to infinity in some direction in the complex plane, basically what would change from before is instead of, before I was just talking about the real and imaginary part of f, or the real and imaginary part of rho, I would just have to replace everywhere I said before the real or imaginary part of f, I would just have to replace that statement with the real or imaginary part of z times f. So we just multiply things by a phase, the exponent. And, well, so we can do the first type of analysis by looking at this limit. Before, so limit, we said that the saddle point was more important. So if we take z to infinity of this ratio of the endpoints to the saddle points, so this limit is 0 as long as the argument of z is less than the arctan of a half. So if z has an imaginary has a phase, then these this e to the 4iz part can be important in the limit z goes to infinity. So whether or not this goes to 0 or not depends on the phase of z. So as long as we go to z goes to infinity with a phase that's less than the arctan of a half, then the saddle point dominates. But if this inequality is violated, the endpoint will dominate. So that's one possible change. But as I mentioned before, the contours also change. They rotate as we change the argument of z, or the angle at which we go off to infinity. So if we do a small rotation, these contours will look, instead of like what I drew before, so here's the imaginary part t, here's the real part of t. So for a small enough angle, the contours will look something like this. But for a sufficiently large angle, the constant phase contours will change, and And these don't meet up. This goes something like that. And the relevant contour will be some contour that goes like this. So there are no saddle points. On the contour. And turns out if you can compute where this jump happens if the argument of z is greater than pi minus the arctan of 2. So there are two possible ways that the asymptotic behavior can change as we rotate phi. So one is that the different terms can exchange dominance, and that happens, I didn't show the calculation, but it happens when argument of z is less than arctan of a half. And also the contours can change. So there's some range of the argument of z for which the contours warp and deform or rotate a bit, but still pass through the same saddle points. So the asymptotics in this case would be exactly the same as before. We just do the same terms. But for sufficiently large argument of z, the relevant contour no longer has any saddle point contributions at all.
So how do we calculate it in this situation?
So what we would want to do is solve. So we're going to solve the equation, the imaginary part of z times rho of t equals constant. So we're going to determine the curves for this, where the constant over here is, or we'd probably want to divide this by absolute value of z, get something finite, where we can compute this by the constant we're interested in. So we want to find the contours that go through the endpoints and through the saddle points. So we would want to, for instance, solve this or plot the equation. Imaginary part of z of rho of t is equal to the imaginary part of z of rho of 1. We want to find the contour that passes through the point 1. Equations are ugly, and these are sketches of plots I drew on Mathematica. In simpler cases, maybe you could draw the curves by hand. We'll look at an example in tutorial where sketching the curves, constant phase curves, or determining the relevant curves is something you can do by hand, but sometimes you might need to look at a computer to determine the right contours. So what we see summarize if the argument of z is sufficiently small, we've got a saddle point dominating. Once the argument of z becomes sufficiently large, we've got an endpoint dominating. And for even larger argument of z, there are no saddles. So this transition doesn't change the asymptotics because the endpoint was already dominating. But in general, when you have a saddle that becomes relevant or irrelevant as we change the phase, that can change the asymptotics. And so we'll see. So far,
A universal phenomenon in the integral that we always have a saddle point dominant and then the end point dominant and then
This-
saddle point disappear.
this is not universal.
Okay.
This is for our case. You could come up with an example where, for some reason, the endpoint dominates, then the saddle point dominates, and then maybe the saddle point jumps off the contour. You could probably come up with an example like that. I don't know of no reason why you couldn't. There's, you could have multiple different transitions in different regions in the complex plane where different asymptotic behavior occurs. Yes.
So if I understand correctly, we always have to plot these at some point to figure out our contours.
You always have to figure out your contours. The example I chose for a lecture, figuring out the contours, I did on Mathematica. So this equation is not something I would want to do on the board or by hand, but some examples, they're simple enough that you can determine the contours just by hand or by looking at them. And we'll see an example in a tutorial where that's the case. Yes, but yeah, the key point is you would get the wrong answer if you didn't deform the contour. Our original contour did not pass through any of the saddle points, and the saddle points, in fact, provide the dominant contribution. This is.
Sorry. How do you determine which saddle point we should use? The I or 5 or 3I?
We use the I exactly because of this plot. So the constant phase contour passes through I. It doesn't pass through 5I over 3.
Okay.
I mean, the 5I divided by 3 does have a constant. The problem is that the constant phase contour of 5I divided by 3 goes up, right?
That's right.
I cannot mix it with the one that goes to -1 on 1, right?
Exactly.
Okay.
That's right.
So we need to calculate a lot of points to determine which contour we should use.
That's right. So in general, you would want to plot the constant phase contours for each of your saddle points and each of your endpoints. Often you're interested in cases without endpoints, but sometimes you want to consider cases with endpoints. If there are no endpoints, usually the calculation is easier, but I wanted to illustrate the general case. So next time, we're going to talk about divergent series. So most of the asymptotic series we've been discussing are, in fact, divergent. Nevertheless, the methods we've seen over the last 2 lectures are some of the most important approximation methods we use in quantum field theory and physics more generally. So tomorrow what we're going to discuss is how to make sense of our answers, what divergent series, or such as asymptotic series, can tell us about the finite quantities that we're trying to approximate. And we'll see some methods in which we can assign a finite number to a divergent series that tells us something, that captures some of the important properties of that divergent series, and in the case of asymptotic series can be used to capture some of the information about the original finite quantity that we were approximating. So this process of assigning a finite number to a divergent series is sometimes called summing a series, although as we'll see tomorrow, we're not actually going to be summing the series. Sum a divergent series, clearly you get infinity. That's in many cases. But we'll see that there is a useful sense in which we can assign finite numbers to the Bernoulli series. So that's where we're going tomorrow. And so I'll see you. Are there any other questions? All right, I'll see you in tutorial shortly.